Hey, okay. Hi, back. Gonna take a quick, quick look at solutions and mixtures. All right, we're still in Unit 3, topic 3.6. We are moving from gases to solutions, and the next few lessons will be on solutions and mixtures. We will then be finished with this topic and this unit, okay? So I'd love to move to new units, but we've still got some work to do before we get there, all right? A lot of this should be somewhat familiar to you and not, but very important content nonetheless. So let me go ahead and share my screen. All right, and if I make, oh, perfect, love it when that happens. Okay, this is a little note to myself about what I need to be sure to cover, all right? So as you see, I start with preparing molar solutions. So we're gonna look at solutions and mixtures, and for the most part, guys, we are dealing with homogeneous mixtures. Homogeneous mixtures are solutions. Solutions are homogeneous mixtures. We're really not too concerned here with heterogeneous mixtures, okay? All right, so you need to realize that the solute plus the solvent forms the solution, okay? And we would have a conservation of mass thing there. We don't necessarily have a conservation of volume. There's no law of conservation of volume. The solute is the substance dissolving. It's always present in smaller extent. And the solvent is the substance doing the dissolving, causing the dissolving, right? It is the solvent moving in and saying, hey, let's pick this solute apart. I'm going to add something to my list, process of solution. I just want to add that to my list. Okay, and so the solute is always present in a lesser amount. The solvent is always present in a greater amount. Water is the universal solvent. Okay, that's just something that's said because so many different things dissolve in water. Okay, and it's most often the solvent that we'll see. Okay, now in the process of making a solution, it is this 3-step process. And this is going to sound weird, but we will see it again. We have step 1, and that is separating the solute, right? So we need that solute to separate, right? We need it to come apart. This requires the input of energy. Well, the way I write it like that, it looks like the energy is coming out of it. Requires energy to be added. You will see this pop up again when we talk about thermochem, maybe. Step 2 is we need to separate the solute. All right? Sorry, the solvent. We just separated the solute. We need our solvent also to separate, right? This also requires energy to be added. Right? It requires an input of energy. All right. So I've got energy added here. I've got energy added here. All right. And then step 3, and all this, well, anyway, is the combining of the solute and the solvent. All right. And that's where you would see your cation surrounded by the anion, the pictures I was talking about the other day in class. And you would see the O here and the 2 H's there. and the O here, and the 2 H's there, and O here, and the 2 H's there, and O here, and the 2 H's there, right? And we would have the 2 H's here and the O over there. So I'm just aligning the water around the cations and anions such that the ion is attracted to the partial opposite charge of the water molecule. Okay, these once again are called particulate level diagrams. And hopefully you realize, right, that this is your partial negative and it's attracted to your cation. This is your partial positive and it's attracted to your anion. Okay, now this process releases energy. Okay, and you guys did, there was an assignment, there was a question on an assignment. I don't remember which one it was. And some of you, I said, well, I'll cover that in later detail. When we talk about whether or not a solute will dissolve in a particular solvent, we like to, there's a common phrase that says like dissolves like, okay? And however, you are not allowed to use that term as an explanation of why does CCl4 dissolve in hexane, but it does not dissolve in water. You cannot say like dissolves like, guys. We need more scientific of an explanation. What like dissolves like means is that polar substances tend to dissolve in polar solvents. Non-polar solutes tend to dissolve in non-polar solvents, all right? Oils are non-polar, do not dissolve in water, which is polar. It's as simple as that, okay? Alcohols dissolve in water. Polar dissolves in polar. Non-polar does not dissolve in polar, okay? Like dissolves like. You can't use that. So let's say that hexane, C6H14, dissolves in, oh my gosh, no, I'm making things up, aren't I? Dissolves in, I think I have too big of a guy here. Let's just say octane. Dissolves in octane, but not water, right? How would we describe that? Well, we would say, this is what you say. Okay, this is what you say. You say the solute interactions. Oh man, this isn't working. Let's just look at it. Let's get rid of this part. Okay. The solute solvent, I'm going to change it and I apologize. The solute solvent interactions are more favorable than the solute interactions and the solvent interactions. Okay, so think about what we just said. And oops, it's really strange. It sounds strange. It even sounds strange to me, but it's accepted verbiage, if you will. Okay, so if we go look up here, what we're saying is the interactions among the solute particles and themselves versus the interactions of, not versus, and the interactions of the solvent particles with themselves are less favorable than the interactions of the solute and the solvent interactions with each other. Okay. So often what we'll see is more energy is released than is put in. More energy is released in step 3 than is put in step 1 and 2. And overall, we have an exothermic process. That's often the case. There are a few cases where it is an endothermic process. That means we have to put more energy in for step 1 and step 2 than we get out in step 3. However, in a few cases, that solution still forms. Okay, and we would then attribute that to something called entropy and not enthalpy, the exchange of energy. Okay. I think if you don't understand what I just said right now, what you do need to understand, because I will elaborate more on that in a different unit, what you do need to understand is how to explain this on a molecular particulate level. Okay. If we were to say that hexane does not dissolve in water, right? Well, then we would say that the solute-solvent interactions are less favorable. Notice what I am not writing is that polar substances dissolve in polar substances. I'm not writing that. I'm not writing like dissolves like. I'm not putting that in my answer. Okay. But the solute-solvent interactions are less favorable than, I know this is wordy, the solute and solvent interactions. Okay. So that's how you're going to handle that. Another thing I could say is I would expect the greater the magnitude of charge here to have a greater attraction for the water. So I would expect more heat to be released, energy to be released. However, the greater that charge gets, the greater the lattice energy is of the solute, assuming it's ionic, and the more likely it is that the water can't overcome that. So I see trends with that as well. If you understand that, good. If not, I'm going to let that go. Okay, so let me look back on my list here. So, okay, now we are going to, there's a lot of stuff on my list. You might have to pause this. I don't know that I'm going to pause it myself though. We're going to look at preparing molar solutions. Okay, very important skill for any chemist or I'd say even nurse, you know. Molar, remember molar? Molarity is the letter M, large M, not a small m, it must be a large M. And I could say 2.5 M, right? I would read that as 2.5 molar, right? So when I see this, my brain sees this, okay? Another way I could write that is 2.5 brackets. That also means 2.5 molar. Both of these mean, all of these mean the same thing. All of these mean the same thing, okay? So that's what I need you to realize is the big M stands for molarity. We call it a 2.5 molar solution, and brackets mean molarity. So I can use brackets in place of my big M, okay? Do not use brackets if you're not talking about molarity though, because it means molarity. All right, and we know that big M is the moles of solute over the liters of solution. All right. Okay. So how do I make a molar solution? Preparing, and yes, there are questions on this on the past few AP exams. They give you a list of materials and you have to describe how you would make a molar solution. In class, I would do the same. So how you're going to make it depends on if you have a solid solute versus a liquid solute. If it's a solid, you need the mass, right? Because I'm going to take that solid, I'm going to put it on a scale, I'm going to mass it, and I'm going to dissolve it in a certain amount of liquid, okay? So let's say how many grams NaCl required I keep NaCl's because it's simple. We know the mass in our head. Required to prepare, let's say that I need 300 milliliters of a 1.0 molar solution. All right, so I need to make it. I need to make it, right? And I do this all the time in the classroom, all the time. Actually, sometimes I get kids to do it for me. I'll be like, can I help you, Ms. Murphy? Yeah, you want to make the solution for me? And it's students like you who I've taught and they know how to do it. So the first thing you're going to do is they need to figure out, this is a solid, right? This is a solid. How many grams of solid NaCl? So I'm just going to take my volume. I'm going to do it the long way. And I'm going to, first of all, some of you already know where I'm going. Some of you don't, and that's okay. This means 1.0 moles. Moles of what? Moles of my solute per every 1 liter solution. Okay? Okay? So I'm going to start with my volume. I'm going to use my molarity to get the moles, and then I'm going to get the grams. So I'm going to say 300.0 milliliters. Right? There's 1,000 milliliters in every 1 liter. And according to my molarity right here, every 1 liter is 1.0 moles of NaCl, right? And then I can just say that every 1 mole of NaCl is equivalent to 58.44 grams of NaCl. So if I do the math, what that is going to tell me, see, that's going to be 0.3 times 58.44. We should be able to do that, get about 30% of 58.44, about 20. You should be able to do that in your head. 17.5. I'll actually keep that in 466, 17.53 grams NaCl. Okay. And I would take that. I'll get to that part next. Let's now look if we have a liquid solute. And in this case, we are diluting. All right, we would be diluting a liquid to a given concentration. So that word right, that bracket right there, this right here, that's a quick way that I write concentration because it's a molar concentration, okay? That's what the brackets mean. So I often just use concentration in my notes. So let's say there's a dilution equation. It's, oops, don't want that guy. This is your dilution equation. You may remember it from last year. And it's actually really easy, okay? And we need to establish something when we're done with this though, okay? So let's say that you need to prepare 250 milliliters of a 2.0 molar HCl from a stock solution that is 18 molar, okay? So as a teacher, I buy a large jug of hydrochloric acid and it's extremely concentrated. And what I can do is I can dilute it and make an amount of any concentration I need. So, and this is where I get the students to do it for me sometimes. So what I need is I need the concentration to be 2.0 molar, and I need to have this volume of it. So I'll plug those into my ones, right? Now I can keep this as a milliliter if I want to. I do not need to convert it, and all it means, and notice that I'm going to get this from an 18 molar solution. So I'll plug that in for this, okay? So all that means is when I solve for my volume, it will be in milliliters because this is in milliliters. So I don't need to convert it. It's going to work. It works itself out. Do the math. That's 250 times 2 equals divided by 18. And I get 27.78 milliliters. Okay, that's easy. Now, how are you going to make the solution? And you will be asked this question, or likely you'll be given a list of materials, and it's a problem like this, and you'll have to describe what materials you would use and how you would make this solution. So the first thing, I think y'all did this, I told y'all this, but you were home for, not all of you did I have. During COVID last spring, we covered this. So you're gonna start with you will use a volumetric flask, okay? Let's see if I can do this. Oh my gosh, that is the best volumetric flask I've ever drawn. You use a volumetric flask. These come in not all shapes, they all have the same shape, but they come in all different sizes. Little 10 milliliters, 100 milliliters, 1,000 milliliters, 2,000 milliliters, all different shape sizes, 250 milliliters, 500. So this one will be a 250 milliliter volumetric flask. And there will be a little mark like that up on the neck. These are very accurate, and that marking is extremely accurate to the 250 milliliters. It's very thin right there. So it rises really high at the end. You have to be careful because it's easy to go over that mark and you just messed it up, okay? What you will do in preparing this solution is you will first put some, you will put some distilled water. Put a small amount of distilled water in the volumetric flasks. And why are we going to do that? A distilled H2O in volumetric. Yes, you need to use the word volumetric because there's an Erlenmeyer flask. There's a round bottom flask. You need a volumetric flask. If you're asked, right? You want the volumetric flask. And we're going to put a little bit of water in there. And that'll be for a couple reasons. I'll tell you in a minute. Next, now what we have to do is we've got to get this 27.78 milliliters of the 18 molar. This is extremely concentrated. How we go about getting the 27.78 milliliters is dependent upon the tools we have at our disposal. Okay, so we could use we could use a graduated cylinder. Okay, we could use a volumetric pipette. Is that what that is? Let me try that again. Then we could use a volumetric pipette. Oh my goodness gracious. That's better. Volumetric pipette, graduated cylinder. I think I'm going to stop the video after this, just so you know. Graduated cylinder, volumetric pipette, and a really great one would be our burette. Okay, and I remember, Ian, you answering the question about that burette one of the first few days of class this semester. Burette. Well, this is going to be the least preferred, right? Most students go straight for the graduated cylinder, and I get that. They're plastic, they're easy to get, they're easy to use, and we use them all the time. But if you don't, right, if this is a real situation, it's really important that you get exactly 27.78, and you're on an AP Chem exam, and you're going to use a more accurate device if it's available to you, okay? I would say go for this guy right here, okay? If it's not an option, go for this guy right here, okay? Because they're more accurate, all right? So the second thing we would use, if we would say use a burette to measure, okay. What was our volume up there? 27.78 milliliters of the 18 molar HCl. Right, so I'm going to get the little bit of the really concentrated stuff. All right. I will, and I'm going to do that using the most accurate measuring device I can so that I can get as close to 27.78 as possible. Now, when you, all of this is stuff you need to know, so I need to tell you, when you go to read your burette, it reads upside down. This will be 0, and this will be 50, okay? So we can imagine 10, 20, 30, well, whatever those are. I wonder if we could make that work. 10, let's just get rid of a couple of those. So we would need 30 to be 40, 30, 20, 10. Let's do something like that, okay? And I'm just trying to get the point across. So my meniscus might look something like this, right? Obviously, it's a little bit big. And right here, right, we would read it. And this would be 20. This would be 30. So we would read this right at about 26.0 milliliters, or whatever it is. Okay, so it reads backwards. It doesn't confuse me, but it confuses some students. Okay, so once we get our appropriately sized volumetric flask, we put a little bit of our solvent, typically it's water, in there. We then use the most accurate measuring device we can to get our particular volume of solute that we need. We will then, I'm down into red now, we will then pour with a funnel if provided, right? Meaning I would put a funnel right here, put myself a little funnel right there, and I would pour my 27.78 milliliters of my 18 molar hydrochloric acid into here. Okay? So pour with a funnel if provided the 27.78 milliliters of 18 molar HCl into the volumetric, don't abbreviate that, flask, the one that has the water, into the water. Now, what's the purpose of putting that water in there? Well, there's a couple things. Some heat will be released when these two, the hydrochloric acid and the water, combine to make the solution. Step 1, step 2, step 3. Step 3 releases more heat, so it's exothermic. That water is there to absorb some of that heat. And if this flask right here were to tip over, instead of being just the 18 molar hydrochloric acid, it's now diluted with some of the water that was already in there. Okay, no big deal. Now, third step, or fourth step, and this is so important that you say this correct way. Fill the volumetric, okay, add distilled water to the volumetric flask until you get close to the line. And I'm going to be specific. What's the line? The 250 milliliter mark. Okay. So I'm going to go ahead and I'm going to add some water, right? I'm going to add some water until I get close to that neck, because at this point it's going to fill up very quickly. I will then use a pipette to add the rest of the water, the rest of the water until you get to the 250 milliliter mark, right? And I'm going to stop in a minute, but let me explain what's important here. It's important that we use a volumetric flask. It's important that we put some of our solvent in there first. We then use the most accurate device as we can to measure out our particular volume of solute that we need. We then add that to the water that's in the volumetric flask. What you do not then do, right? So at this point, we're sitting just like this. We've got our flask that is not as good. We've got some water in it, and we just added our acid to it. And here's our mark. You do not add water until you get to the mark. Actually, that is exactly what you do. You do not add, this is what you don't do, right? We need a 250 milliliter solution. We added 27.78 milliliters of HCl. If I subtract that, I get 223.22 milliliters of water. Okay, that is what you do not do. There's no law of conservation of volume. So you do not subtract this and say, now add 223.22 milliliters of water. Don't say that. Don't even subtract. Just say add the water until you get to the mark. That's how much water you add. However much water you need till you get to that mark. Okay? It's important that you say that. And you don't say add this much water. You add as water until you reach the mark. Okay? So let's review what we've looked at here. And what we didn't look at here. So we did talk about preparing molar solutions, both with a solid when we need to get the mass, and we would use a scale for that, and a liquid where we use our M1, V1, M2, V2 equation. We talked about how to read a burette. We talked about the step 1, step 2, step 3 process of forming a solution, process of solvation, it could be called. We talked about the fact that solute and solvent makes the solution. Water is the universal solvent. There's our 3 steps. And we talked about the words in the vocabulary and how to describe the process of making the solution in the volumetric flask, and the fact that we use the most precise glassware possible and that we fill it up to the mark. We don't add a particular amount of water. Okay, so I'm going to leave that there, and then I'll make part 2 of this video, and we'll finish it up. What do we need to finish that up with? Oh, molarity. Okay, that all goes together. Dissociation, molarity, particulate. All right, great. So I'm going to stop. I'm going to end.